Okay, can people hear me out there?
Yes.
Oh, good. We're in a different venue today, so. Okay, maybe we should start class. So the first thing I'd like to kind of make sure people understand is the homework schedule and also the final exam schedule. So, there's only one, I believe, homework assignment left to turn in, and that's homework number 12. Okay, so that should be listed on your syllabus over here, and it's these 4 sections. So what we'll do is we'll cover most of the material. We'll probably finish all the material by the end of the week. So you should have time to finish up your homework. It's going to be due on Tuesday, December 8th. Okay. And so there'll be 12 homework assignments total, and we'll drop the lowest 2 of your homework scores. So the highest 10 will count, we'll total them up, so everything will be out of 100 points. Okay. And then in terms of final exam, the final exam is December 11th from 12 to 3 p.m. So this is the final exam that is scheduled for our time period. Monday, Wednesday, Friday from 12:40 to 1:30. Okay, we're not going to deviate from that because otherwise it might mess everyone else's schedule up. Okay. Are there any questions up until this point on this? All right. What I'll do also is I will send you an email probably by the end of the week in terms of the procedure for the final exam. What we'll have to do is we'll have to log in early so I can check IDs, and we can also make sure everything is set up correctly. I will have to email you the final, and then you can either take it on paper or you can take it on a tablet. And if you take it on a tablet, you write your answers just like you normally do, and then you'll email your final back to me. Sorry. And if you decide to write it on paper, you'll have to scan your exam and then send it back. Okay. All right. Okay, so let's go back. All right, so today what we're going to do is we're going to continue on with the Gram-Schmidt orthogonalization process. All right. So what I'd first like to do is I'd like to review for you the Gram-Schmidt process. So remember what the idea was. You have a basis for a subspace and you want to change it into an orthogonal basis. Okay. So let's call it x1, x2 up to xt be a basis for W subspace of Rn. Okay, so these vectors may not be orthogonal to one another, but we want to straighten them out by using projections. So what's the idea? So the first thing is we want to set V1 equal to X1. Okay, so here is V1, which is also X1, and your vector X2 may not be orthogonal. So what we do is we project X2 down onto X1, and then we take the part which is orthogonal to that. So the idea is we want to project down. We know how to do that, and then we take X2 minus that. Okay, So once we do that, V2 was X2 minus the dot product of X2 and V1, V1 with V1, and then V1. Okay, so this vector here at the end is just the projection onto X1, and then V2 is just X2 minus that projection. And that gives you this vector over here. Okay, any questions on this? All right, now what we do is we just continue the process. So if we have two vectors, now V1 and V2, and then we have X3 over here, which goes like this, let's say, then what we want to do is we want to do a projection and take this vector over here. So we want to project onto the subspace generated by X1 and X2. Let me make this picture a little bit better here. Okay, so actually, let me redo the picture. This is a crappy picture. Sorry about that. Okay, so let me draw this a little bit better. So here's a V2, and let's say this is V1, okay? So you have this plane, which looks something like this, which is spanned by these two vectors. And your X3 vector is not going to live in the plane. It's going to live somewhere out here, but it may not be orthogonal. So the idea is you want to project the X3 vector down to the plane. And we have a formula for the projection. And the V3 vector will be the vector out here like that. Okay. So V3 is going to be equal to X3 minus X3 V1, 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 minus X3 V2, V2, V2 of V2. Okay. And then finally, your last one, you can see what the pattern is. So you're going to take X of t, and you're going to take the dot product of X of t with all the other previous vectors. So xt v1, v1, v1 times v1 minus xt v2, v2, v2 times v2 minus xt vt minus 1, vt minus 1, vt minus 1 times vt minus 1. Okay, so at the end, v1, v2 up to vt is an orthogonal basis for the subspace W. All right. Any questions on this? Okay. So let me review the example that we did. I'm not going to go over all the details. I'm just going to give you the answer. So we did an example last time. So the example was using the Gram-Schmidt process. Find an orthogonal basis for the following vectors. 3, 1, minus 1, 3, and then minus 5, 1, 5, and 7, and 1, 1, minus 2, 8. Okay, so these are vectors here. So we're draw them like vectors. Okay. All right, so we actually calculated this example using the Gram-Schmidt process, And we're able to find an orthogonal basis. So this is from last time. And what was the orthogonal basis we got? Well, the first vector has to be the same. The second vector was 1, 3, 3 minus 1. And then the third vector was minus 3, 1, 1, 3. Okay. And if we want something which is orthonormal, we just divide by the length. So if we want an orthonormal basis, well, the length of each of these is what? 3 squared plus 3 squared. Yes.
Root 20.
So what's the length of these vectors? Anyone?
Root 20.
Root 20. Okay. So I have to divide by root 20. Thank you. Okay, let me just make sure I didn't get the signs messed up here. So 1, 2, 3. So I'm just checking really quick. You may want to check your notes too. Oh, I have a minus 3 here. Okay. Does that look okay? All right. Okay, so this was an orthonormal basis. All right. Now, it turns out you could do the following. So I want to talk about something called a QR factorization. And we'll come back to this example in a second. Okay, so it says the following. So let A be an M by N matrix with linearly independent columns. Okay. So if we have that, so think of if we have linearly independent columns, we can look at the span of those columns, and that's a subspace. And because the columns are linearly independent, they form a basis for the column space already. Okay. So W is just the column space, and we can apply the Gram-Schmidt orthogonalization process, and we can actually do a matrix factorization of A. So then A is going to be Q times R, where Q is an M by N matrix with orthonormal columns. Okay. And R is an upper triangular matrix which is invertible. With positive entries along the diagonal. Okay. So the point is that we can actually find this Q by using the Gram-Schmidt orthogonalization process. And then once we use the Gram-Schmidt, we divide by the lengths to get orthonormal columns. And then we just put that in, and then we can actually find the factorization this way fairly easily. And that's what I'm going to show you how to do next. Okay. So let me just give you a little bit of justification why this works. Okay. So first of all, we just let A have columns x1, x2, let's say up to xn. Okay, so these are the columns of A. They're just vectors which are down the columns, all right? Now, we know how to use Gram-Schmidt on the columns. So we can get U1 up to UN, which is orthonormal by the Gram-Schmidt process. Okay. So just like what we did up here, whoops, in the example. Oh, what's this? Sorry about that. Hang on, let me just go out of here and then go back in. Okay, that's fine. All right, so what we did was we used the Gram-Schmidt to actually get this orthonormal basis down here. Okay, so we'll use this example in a second. All right, so why don't we let Q be the matrix with the columns being the U's. Okay. Now, what's the relationship with the X's and the U's? Well, we know that the span of x1, x2 up to x sub k is equal to the span of u1 up to u sub k. Okay, so like if you look at the Gram-Schmidt process, at each stage here, like let's say I'm looking at just V3, then I'm only using V1 and V2 there. So the span of V1, V2, and V3 is the same as the span of X1, X2, and X3. Okay. Now, moreover, what else do we know? Well, we know that the xk here, the vector xk, is r1k u1 plus rkk uk. And this number here is always bigger than or equal to 0. Actually, it's strictly bigger than 0. Okay. So what we can do is we can actually order the r's here. So r is going to be equal to, whoops. Okay. So R will be just the matrix with R1. Man, it's not my day. Okay, R1, R2, up to R sub n. Okay, so the R's are just these coefficients over here. Okay, and then A here is equal to Q times R. Okay. So that's basically the idea of what's going on. All right, now how do we put this into practice? Okay, so here's the example we're going to do. Is let A be equal to the matrix 3, 1, minus 1, 3, minus 5, 1, 5, 7, and 1, 1, minus 2, 8. Okay. So the thing is we want to find the QR factorization of A. Okay, now let's look back at the example here. So notice that back in the example, we have a basis, and this is exactly the columns of A. Okay, so the columns of A correspond to the entries or the vectors over here. All right, so now to find Q, what should we use? Anyone?
Gram-Schmidt.
Okay, so we use Gram-Schmidt, but given what I've shown you up here, I mean, what should we use for the Qs for Q? So remember, these are the columns of A. All right. So what should we make the columns of Q?
Is it the vectors in the orthogonal basis?
Is it the ones in the orthogonal basis or the orthonormal basis?
Orthonormal.
Orthonormal. Okay. So we want it to be an orthogonal matrix, so it has to have orthogonal columns and rows, right? All right. So now we just set Q to be equal to 1 over the square root of 20. And then I have to put in those things. Now I have them written down someplace, so I can just do that. So 3, 1, minus 1, 3. Let's make sure I'm not making any errors here. 1, 3, 3, minus 1, minus 3, 1, 1, 3. Okay? All right, good. So we know that A is equal to Q times R. Now, what I'd like to do is I'd like to find out what R is. Okay, so how do we find R? Is there something we know about Q? I mean, like, do we know what the inverse of Q looks like? Anyone? So remember, Q has orthonormal columns. So what should the inverse of Q be? Okay, any guesses? Now, if we want to find the inverse, we could use like Gaussian elimination if we wanted to, right?
Isn't it impossible to find the inverse because it's not an n by n matrix?
Sorry, I have to be a little bit careful. Okay, so maybe I should be a little bit careful. Sorry about that. You're right. You're right. It's not an n by n matrix. All right. So here's the point. It's almost like an inverse. Okay. So I want to multiply. Yeah, if it was square, everything would be good. Okay. So now multiply both sides by Q transpose. Okay. So then when I take Q transpose A, this is equal to Q transpose Q times R. Okay. And it turns out that when I take Q transpose Q, I do get the identity matrix. Okay, so I get a 3 by 3 matrix. Let's just check whether this is right. So here I get this is 4 by 3 here, right? And the transpose is 3 by 4. And the identity matrix here is a 3 by 3 matrix. Okay, and that's because again, you know, your rows are going to be orthogonal, or your columns are orthonormal. So when you take the dot product of the row with any of the columns, you know, you're going to get 1, 0, 0, and then 0, 1, 0, and et cetera, et cetera. Okay. All right, so this is the identity. So that means that Q transpose A is R. Okay, so that's really nice. And so now we can actually compute things out. So R is Q transpose A. So Q transpose is 1 over the square root of 20. And let's just take the transpose of this. This is 3, 1, minus 1, 3. Okay. 1, 3, 3, 1, and minus 3, 1, 1, 3. Okay, so I want to write that, that's Q transpose. All right. And now I just write out what A is. Let's write out A here. That's 3, 1, minus 1, 3, minus 5, 1, 5, 7, and 1, 1, minus 2, and then 8. Okay. So I get 1 over the square root of 20. And let's start taking dot products here. Okay, so what's the size of this matrix going to be? Anyone? How big
4
is
by
R?
4?
R?
3 by 3.
Yeah, it should be 3 by 3, right? Because so this is a 3 by 4 matrix, and this is a 4 by 3 matrix, and so it's 3 by 3. Okay. All right. Let's take the dot products here. Okay, so the first one is just going to be 3 squared plus 1 squared plus 1 squared plus 3 squared, so you get 20. Okay. And the next one should be minus 15. So I get minus, so let's see, let's get this right. So minus 15 plus 1, that's minus 14, minus 5 is minus 19, plus 7 is minus 12. Is that what people get? Yes, no?
Yes.
So minus 12, right? Okay. So next one is 3 plus 1, that's 4, plus 2 is 6, plus 24, and that's 30. Okay. And the next one is going to be orthogonal to that, so it's going to be 0. Everyone all right with that? And next one's minus 5 plus 3, that's minus 2 plus 15 is minus 13 plus 7. I say, yeah, is that 20? Is that right? Has to be
Isn't
positive.
that negative 5?
Let's try it again. Minus 5. So let's try it again. Minus 5 plus 3, that's minus 2, plus 15, that's 13 plus 7, and I get 20.
So it is 20.
20, okay, good.
Isn't it positive? Yeah.
Last one. 1 plus 3, that's 4. Minus 6, that's minus 2. Plus 8. Okay, plus 8 is going to be 6. Is that right? Okay, 1 plus 3, that's 4. Minus 2. Yeah, should be right. Okay, so this next one is orthogonal, right? Okay, so let's check the next one. So I get 15 minus, yeah, 15 plus 1, that's 16. Plus, oh, let's see, is that right? 15, 1. Should get a 0 here. 15 plus 1 is 16. I seem to get a non-zero entry. Oh, there's a minus 7 here. Oh, God, did I screw up? Yeah. There's a minus 7 here. All right, so let's check this over again. Sorry, 1, 2. It's one of these, it's those Mondays. So, okay, there's a minus 7 there. Okay, so let's just make sure we get things correct here. Okay, we'll get it right, but it'll eventually turn out. Okay, so let's go back. Okay, so there's a 3 here. Okay, let me just check the matrices really quick, just to make sure they're all correct. Okay, all right, so that one's okay. So this number better be checked again, because we dotted with the second one. So we better check this guy again, all right? So what do we get? We have minus 15 plus 1, okay? So that's minus 14, minus 19, okay? And then I get minus 21, is that correct?
Yes.
So what do I get total?
Negative 40.
Okay, negative 40. All right, good. All right, so the next one should be okay, and then this one, and then we have to do this one times that one. So what do we get? Minus 5. Okay. So plus 3 is minus 2 plus 15. Okay, it's minus 5 plus 3 is minus 2 plus 15 is 13 minus 7 is a 6. So let's do, we get a 6 here. Nope. Okay. All right. Okay, I assume the last one's all right. Okay, then we get a 0. Now let's recheck this one over here. So what do we get? We get 15 plus 1, which is 16, plus 5 is 21, minus 21 is 0. Okay, that's what we should definitely get. All right, and then let's do the last one. Minus 3 plus 1, that's minus 2. Another minus 2 is minus 4 plus 24, and I get a 20 over here. All right, so you should definitely check this work. But okay, so that's how we get R. All right, any questions on this? Okay, so notice that R here is upper triangular. It's also invertible. And there are positive entries on the diagonal. Okay, so it's all the things that that we said that it would actually be. All right, any questions on this? Okay, good. All right, so the next thing I want to talk about are what are called projections. And so I just want to actually put this in a different light. So we've actually seen this before, but I want to sort of be able to think about it in a different way, because this will help in terms of our analysis on least squares. All right, so here's the idea. So I have a vector A over here, and I have a vector B over here like this. Okay. Now, we have a formula for the projection, okay? So if I want the vector which is projected orthogonally onto this thing, so P is going to be equal to some constant times A. We know what this D is. It's just given by inner products. So there's a formula which we derived. So P is going to be equal to the inner product of A times B over A times A times the vector A. Okay, so this is just the projection formula. Now, what I want to do is I want to write this projection formula in a different way in a vector notation. Okay, so let's write this in terms of vector notation. So P here, well, what is the dot product? It's just basically A transpose B. And then down here is A transpose A times the vector A. Okay. So, so let's do an example where we do this. Okay. So project the vector V equals 1, 2, 5 onto the vector W, which is going to be equal to 3, 5 minus 1. Okay, so let's just apply the formula. So the formula is P. So we want to project on the vector W, right? So this is W transpose V times W transpose W times W. Okay, so let's figure out what that is. So what's the dot product between W and V? Anyone?
7, 8,
Let's- 8. Okay, let's see. 3 plus 10, that's 13 minus 5, that's 8. Okay. What's the dot product between W and itself?
23,
Strike. So it's 9 plus 25,
33,
35.
Four?
34. Or
Yeah, I know it's
33.
35, yeah.
35. Okay. Yeah, I know. It's after like Thanksgiving weekend. It's like not good for any of us. So, all right, and then I just put in W. Okay, so we can't compute dot products, but we'll get better. All right. Okay, is everyone all right with that? Okay, so that's how we project. Now, what I want to do now is I want to actually find a formula. And so I can actually find a formula which tells me how to project any vector on a W. Okay, and I will just do it by finding some matrix. Okay, so let's look more closely. Let me just rewrite the formula here. P is equal to A transpose B and A transpose A times A. Okay. Now, A transpose B times over A transpose A, that's just a scalar. So I can move it to the other side without any problems. So this is going to be equal to A, and then I could do A transpose B times A transpose A. Okay, it's just a scalar. I just move it to the other side. But remember, matrix multiplication is associative. So what I can do is I can write A transpose over A transpose A times B. Right? And so this matrix here is called P. So P, which is A times A transpose over A transpose A, is what's called a projection matrix. So once I actually compute the projection matrix, then I can actually compute the projection of any vector onto B. Sorry, anything onto A. So P projects any vector onto A. Okay, so it could be, you could just pick a vector, just apply the projection matrix, project it onto the vector A. All right, now, what are some properties of projection matrices? Okay, so before we do that, I think we should probably do this example. Okay, so let me, actually, I'd like to do the example first before we state the properties, just because we just want to do a little bit of a reality check. Okay, so let's go back to this example over here. Okay, so what are we doing? So the A vector is W. So let's do an example. So the A vector is going to be equal to, 3, 5, 1. Maybe it was 3, 5 minus 1, okay? Okay, so we're going to try to project onto W here, and W is just A, right? So let's compute P. So this is going to be A times A transpose A. All right, so let me just do that. So, so this is the vector 3, 5, minus 1 times the transpose 3, 5, minus 1. And then we computed the dot product before as 35, right? Okay, so we have 35 down on the bottom. Okay. All right, so let's compute this out. So it's 1 over 35. And now we just take matrix multiplication. So you take 3, the top row, and you take it times the vector 3, 5, minus 1. So I get 9, 15, minus 3. Okay? And then you take the 5 and you do the same thing. So that's 15, 25, minus 5. And the last one is, of course, minus 3, minus 5, and 1. Okay? Does everyone see how we did this? So you actually get a matrix. And if I want to take the projection of a vector, I just apply the matrix to the vector and I get the projection that way, right? Okay, so so here's some properties. Let me list a few of them and we will go over some next time. So you can just see the example. So first of all, P is symmetric. Okay, so you can actually prove that. So notice that this matrix is symmetric, right? It's equal to its transpose. 2. If I take the square of the matrix, I get P back again. Because if I project, so if I take something like this, and if I project it onto A, I get this vector, which is in the span of A. If I project it again, I don't go anywhere. Okay, so that's where I take it twice, I just stay put after one time. So that's why P squared is P. And this means that the matrix is what's called idempotent. And the rank of P, well, so 3. The rank of P is 1. Okay, so notice that if you take any row in this matrix, it's a linear combination of the first row. And so the rank has to be 1. If you use Gaussian elimination, you're just going to get the top row. And then what is the column space? All right, so what's the image of P? Anyone? What does P do to the vector B? What's the dimension of the column space? Anyone?
1.
1, okay. So it's one dimensional. And so it's going to be spanned by a vector, right? So what vector is it spanned by?
P.
It's what?
Vector P.
It's spanned by, sorry, just look at the picture over here. So this is the projection given by the vector A. Okay, so if I project any vector, it's going to be a combination of A, right? It's going to just be a scalar times A. So it's in the span of A. It's equal to the span of the vector A. Okay, does that make sense?
Yes.
Good. All right, great. Okay, so that's all I have in terms of projections and QR factorizations for today. Next time I'll talk about least squares and we'll do some examples. And we'll do plenty of examples. Now take us to the end of the week. Okay, any questions up until this point?
Do we have class tomorrow?
I think we have class on Wednesday.
Okay, for some reason my calendar had class tomorrow, but I might have just added that.
Okay, so I think the schedule is we have class Monday, today, Wednesday, and Friday this week. All right. And then next week we have class Monday, Tuesday, Wednesday.
Okay, that was it.
And then we have the final exam on Friday. So what I would really like to do is I'd like to finish the material for the course this week. So you have, time to sort of get ready and study for the final exam. So I'm going to devote Monday through Wednesday next week towards review. Okay, does that sound?
Yeah, I had one more question about
Sure.
getting the matrix above there. So we multiplied each element by 3, 5, minus 1 to get the matrix.
Yes, that's right. Because you're taking the first row and then you dot it with each entry. So you're
Okay.
taking the 3 here. I have to take the dot product with 3, with 5, and then minus 1.
Okay.
It's a one by one mate.
Yeah.
One by
it's a-
one.
Oh, okay. Oh, so you have a dot up in the numerator and then you
Right,
just
right.
wrote, okay,
Yeah.
I see.
That's what it is, right? It's a clever little trick. You know, you can actually write the projection matrix. And then you don't have to keep on doing projections, you know, use the formula all the time. Once you have the projection matrix, you can project anything you want.
Gotcha. Thank you.
Good. All right, other questions? Okay, so if not, I will see you on Wednesday then.
Thank you.
Welcome. Have a good day.